Every day, new vulnerabilities threaten critical infrastructure, yet organizations rely on outdated manual security measures that can't keep up. The rising complexity makes real-time threat mitigation nearly impossible, leaving security teams reactive instead of proactive. We knew there had to be a better way, one that enables real-time risk assessment, automated decision-making, and intelligent cybersecurity. That's why we built GraphMind AI, MCP-powered agents for cyber intelligence. Our team, Mantanta Revuri, Raghuram Vadlamani, and myself, is here to transform cybersecurity defense. As software engineers working with knowledge graphs and LLMs, we recognize the potential of intelligent automation to deliver cost-effective, accurate, and efficient search results in cybersecurity. Cyber threats don't impact individuals, they can cripple entire industries. Our goal was to build a resilient, next-gen agentic application that safeguards critical systems. The CVE dataset holds a goldmine of insights on newly discovered vulnerabilities. By leveraging it effectively, we can predict and neutralize threats before they strike. We applied first principle thinking and used multi-agent orchestration to create a system that is scalable, adaptive, and resilient. By combining ArangoDB's multi-model capabilities, LangGraph's AI workflows, and Model Context Protocol, MCP, we are pushing the boundaries of graph-powered cybersecurity intelligence. Coming to the problem statement, the cybersecurity industry faces three major challenges that must be addressed. The CVE dataset has grown to over 145K vulnerabilities, and security teams still struggle to keep up. Most security solutions rely on periodic scans and manually created data, creating blind spots that hackers exploit. So, without a system that can process, analyze, and act on security vulnerabilities in real time, organizations are left vulnerable to evolving threats. That's why we have a need to automate intelligence. The CVE dataset is the foundation of modern cybersecurity, providing a structured way to track and analyze vulnerabilities. But before we go ahead and talk about why we opted this dataset, we initially faced some challenges. The given dataset provided for the hackathon that we imported had inconsistencies, and all the vendors were pointing to a single product, making it difficult for us to establish accurate relationships. We corrected this by creating and restructuring the data, ensuring an accurate representation of vendors and products. The CVE dataset contains over 145K nodes and 316K edges, making it difficult to navigate and extract meaningful insights. It is also recognized by the National Vulnerability Database, and it is widely adopted across cybersecurity frameworks. And this dataset provides severity scores, affected products, and detailed references, making it invaluable for cyber threat analysis. And it is also an open source dataset, and it fosters community-driven improvements in cybersecurity defense strategies. So this is the process loop that we figured it out in order to harness the power of native multimodal capabilities of ArangoDB, LangGraph, and MCP. So we structured the CVE dataset as a graph in ArangoDB, ensuring relationships between products and vendors were accurately mapped. We used LangChain agents and developed a natural language interface that allows security teams to query vulnerabilities dynamically and retrieve relevant CVE data instantly. We implemented GPU-accelerated graph analytics to conduct centrality analysis and community detection, helping security teams prioritize more on critical vulnerabilities. And our MCP-powered dashboard delivers real-time AI-driven visualization that can help security teams understand, analyze, and mitigate these threats with ease. An important note here is based on the user's intent, we can fully leverage the out-of-the-box capabilities of LLMs to change the visualization based on user's intent. So this is a high-level architecture diagram that we built for this application. We are utilizing LangChain React components on the right section of the screen within a Jupyter notebook, where we have configured a variety of tools to take full advantage of ArangoDB's multi-model capabilities. First, we created a tool specifically for answering queries related to Arango query language by using ArangoGraph from LangChain. Alongside, we have developed custom tools to handle Arango search and generate network X code. So our agent is also designed to perform hybrid query searches based on the context of the query. So these tools pull data directly from ArangoDB's persistence graph, and the results are displayed as markdown within the notebook. So for interactive elements, we are leveraging Cloud's dynamic artifact generation, which is powered by a custom MCP server to communicate with Jupyter Notebook using the out-of-the-box capabilities of LLMs. Now, without further ado, let's hop on a demo and showcase how we built next-gen agentic application with GraphRag and NVIDIA cuGraph solution that makes vulnerability management smarter, faster, and more efficient. Alright, this is our notebook that we created for our hackathon. We are using Tesla T4 GPU, and we installed all the necessary packages that are required in order to run our application. And we are using Anthropic's Cloud model, 3.7 Sonnet model for our entire activity. Here we are creating a database instance, and then we are ingesting the dataset, CVE dataset. So I already told you earlier that we were facing some issues as the product vendor relationships were broken, and we tried to manually fix it and change those files. And then here we are establishing a connection with the graph. And then you can clearly see that we are creating a view for performing Arango search, full text search. And then this is the output generated. So we are using Arango search tool functionality to perform proximity, full text search, fuzzy matching, token search, calculating BM25, etc. using this tool. So this tool is used to convert natural language queries into AQL queries for Arango search. And then we are declaring graph instance. And then we are verifying all the config files, whether we are using cuGraph or not. And then this is the graph schema that we received. Now let's go to ArangoDB web interface to see how exactly our graph looks like. So this is a sample of a graph that we ingested. And these are the statistics, the total number of nodes and edges. So here we created a tool for text to SQL Arango search. It is used to invoke and interact with ArangoDB directly and perform a full text search based on user's natural language query. And it converts SQL supported full text search query and executes the query and translates the result to natural language. And then here you can see that we created another tool to translate it to text. And then here we created another tool for network X code generation. So in total, this tool utilizes 3 different types of prompts to handle code generation, optimization, and corrections. So initially, it gives a detailed prompt using the provided instructions, schema, query, and graph stacks. Then the generated code is optimized in the next step to make sure time constraints and sampling are in place. Next, the code execution takes place, and on success, it will return the info to the LLM to summarize. So in case of a failure or error, all the initial details are used to create a code fix prompt, and then it gets passed to LLM for multiple attempts and for previous errors as well. So here we wrote a detailed prompt which caters performance optimization, execution constraints, and tells in brief how to handle large graphs, how to do sampling, and you can clearly see that how to do library selection too before code generation. And then this is the refactoring code that we used to resolve the issues, and it will be sent to an artifact, cloud artifact. And then this is a React agent that is created to answer these queries. So this agent has access to multiple tools to perform different types of operations and analysis on the graph. This agent supports both single and hybrid calls based on the user's query for explicit directions. And you can clearly see we have 3 tools here: text to equal to text, text to network X algorithm to text, and text to equal Arango search. And here is the detailed system prompt that we wrote. And then below are the following examples that we asked to test the functionalities. So you can clearly see that for which vendor has more CVs, it entered the ArangoGraph QA chain, and then it wrote the equal query, and it gave the result back. And then it added some context based on the data. So we did it iteratively for all these queries, and we can clearly see that how text to equal Arango search is working. And then we have a functionality to showcase here that whether multi-tool calling is enabled or not. So for these use cases, it is not. So for this example query for network X code generation, you can see that the query asked by the user is to calculate modularity scores to understand the structural integrity of these vulnerability clusters. But then you can see that the code generated has a lot of errors, and it says subgraphing is not yet implemented. But then the LLM understands what the problem is, and then it tries to refactor the network X code to resolve the issues. And you can see it's attempting. And in its initial attempt, it figured out what exactly the issue is, and it gave us back the modularity scores. So we did for all these user queries. Now, without wasting time, let's show how we can do natural language query in real time. And before, I just wanted to tell you that we initialize the server on ngrok, and this is the development server running. So what we are doing here is we are using cloud, but then in order to use it as our UI, we created a custom model context protocol server which communicates with the Jupyter notebook for sending API requests, and on receiving the results and artifacts, this cloud will use that information to create the visualization. As we have time constraints, I will go through the queries that we already asked our ArangoDB agent. So this is a sample question that I asked: what is the influence of the word cross-site scripting on the CVEs, and draw the results as a directed graph. So you can see that it created this rich interface with an overview, and these are the 3 tools that it used. And this is the graph that it rendered along with the legend. This is the statistics, timeline, and code. You can see that this is the network X code, and this is the ArangoDB query code. Now let's see the other question that we asked: CVEs containing key security terms. Okay, this is something, we got an error, but let's go up. Okay, so you can see that we asked for how many CVEs have the following words: attack, vulnerability, remote server, authenticated, cross-site scripting, CSRF, injection in their summaries, and to list the total count as a bar chart. You can see that it did it exactly. And then this is the data table, and this is the query that it wrote. You can see that it's calling the search functionality. Let's see this question. Okay, what are the top 5 products in terms of numbers of CVs, and which of them is integral to the network? And this is the dashboard that it created. It's calculating the AQL query. It's doing network X analysis, and it came up with the most central product as Debian. And this is the entire summary, and these were the key findings, and these were the tools that it used. Super cool. Let's see this interesting question: which vendor has more products? Okay, so this is the query that it generated. This is the first query, and this is the second query, and these are the results that it populated. And this used 2 tools. Now let's see this interesting question: visualize the artifact, and network code should be displayed. Okay, interesting. It's calculating the betweenness centrality. It came up with these top 5 vendors. This is an interesting question that it created for vulnerability spreaders. Thanks a lot for watching the demo. Take care. Bye-bye.